Right. Good afternoon, all of you. In this session of mechanical properties of fluids, we'll discuss about the flotation concept, mechanical properties of fluids in this. So this is the session 7 as of now. So this is the flotation concept. Are you able to see the heading flotation?
Yes, sir.
Right. So what is this flotation means? First of all, you can see a simple diagram you can understood. Suppose a tumbler with some liquid is there, then the liquid is filled up to a certain level. Now I can keep an object, okay, on the liquid, this object, let us say. So what are the forces acting on this object? First of all, I think as of now you understood. Suppose this object has mass m, then the forces acting on this object is vertically downwards weight 8 mg is acting. Vertically downwards weight mg will acting. That is gravitational force. And vertically upwards mg is acting. Buoyancy force will acting vertically upwards. Okay, that is the force of buoyancy. So that we can name it as Fb. These are the forces. Okay, so that means this mg makes the body to sink down into the fluid. Sink down into the fluid, whereas Fb buoyancy force will make the body try to float on the fluid or on the liquid. Okay, that difference you can understand. So in this situation only, let us imagine the density of the solid is you can say rho. Okay, and the density of the liquid is let us say sigma. So rho will be the density of the solid and the density of the liquid is sigma. This is the density of solid body. So density of liquid density. Now the body is said to be rest, suppose, in the static liquid. That means it is floating. Then what you can imagine? Suppose the volume of the body, solid body is capital V. Then definitely if the body is floating means the buoyancy force Fb will balance the weight of the body. Buoyancy force Fb will balance the weight of the body. Then only we can say the body will floating on the surface of the liquid partially or fully. Suppose if the weight will be greater than that of buoyancy force, then the body will sink down to the bottom of the liquid. Or if the weight is less than the buoyancy force, then this will completely float on the surface of the liquid. So that means there are three cases will come to the line here. So then actually the body is in equilibrium. What type of equilibrium here with respect to liquid? Translatory equilibrium. So here actually in flotation there are two types of equilibriums will be there. First equilibrium is a translatory equilibrium. Translatory equilibrium. And second, another type of equilibrium is rotatory equilibrium. Rotatory equilibrium. Okay. So in translatory equilibrium, very simple. First, one by one, we'll discuss. First, we'll go for translatory equilibrium. So in translatory equilibrium, the weight of the body, solid body, should be balanced the buoyancy force. Weight of the body should be is equal to Fb on the liquid surface. So what is weight of the body? You can calculate. Weight W is equal to mg. Okay, are you able to follow it? Where m we can write as density. What is the density of solid? Rho. Density into volume into G. Rho Vg. That is the weight of the body. And FB buoyancy force, what I said? Buoyancy force is the weight of the displaced liquid. Weight of the displaced liquid. That I can write as sigma density of the liquid into volume displaced. Suppose if it is fully immersed, then full volume you can take. Suppose if it is fully immersed, suppose, and floating, then total volume that is displaced is V, full volume into G. So that is the buoyancy force. Are you clear this? So weight is rho Vg, Fb is sigma Vg. V is the volume of solid only. So this actually this upthrust force we can, this buoyancy force is also called upthrust force. This buoyancy force is also called upthrust force. Upthrust force means force acting upward direction to make the body to move up or lift upside. To lift upside, that is the upthrust force. So that here the buoyancy force will act like a upthrust force. So when it will be equilibrium, the upthrust force will balance the weight. So that is Fb is equal to weight, or upthrust force will equal to buoyancy force. Anyway, you can write. Okay. So in such a case, what it is equal to? Rho Vb weight is equal to sigma Vb. That means it is indirectly depends on the densities only, na? Density of the solid and density of the liquid. So now case 1. Suppose if density of the solid, if rho is greater than sigma density of the liquid. This is the solid density, this is the liquid density. If the density of the solid rho is greater than density of the liquid sigma, then what happens? Density of the body is greater than density of the liquid. Then what happens? This weight of the body will be greater than upthrust force. That implies weight will be greater than upthrust force. So if weight is greater than upthrust force, what happens? The body will sink down. The body will sink down and it will reach to the bottom of the container. It will reach to the bottom of the container. How we can imagine the final situation? I will draw the diagram. The final situation will be like this. So this is the container of liquid. Then the body will be at the bottom. You can see like this. It will reach the bottom. Are you clear this? The body will come to the bottom and sink down at the bottom of the liquid. So this is for condition for sinking into the liquid. Condition for sinking into the liquid. Are you clear this up to? In translational equilibrium, translator equilibrium, if the density of solid is greater than density of the liquid, then weight of the body is greater than upthrust force, then the body will sink down to the bottom of the liquid and there it will stops. Because at bottom we have some metal rigid body, na? So that's why it is stopped. Next case 2 will come. Case 2, if rho is equal to sigma, density of solid is equal to density of the liquid. That implies weight is equal to, weight of the body exactly is equal to upthrust force. Weight is equal to upthrust force. Okay. So in that case, the solid body simply floats into the liquid, and that too, how it will float? Float in just inside the liquid. You can imagine like this. It will float like this. That means it will completely immersed, because total volume I have considered na, for upthrust here in this case. In that case, you can imagine the solid body will be like this. Since still it is floating only, but it will float just inside the liquid and it will touch the surface of the liquid. Are you clear the second case? If rho is equal to sigma, weight is equal to thrust force, and that also total volume will be immersed and still floating. Still it is in condition of floating. Are you able to follow in, my dear students? Second case, if rho is equal to sigma, density of solid is equal to density of liquid, then it is completely immersed and it is floating. Have you observed this is a real-time case? So this first case, real-time cases, you can take any a metal. First case example, you can take any metal body, and simply you can take like a knife, or you can take like a rod, like a screw, metal screw, simply, or a stone, you simply throw into the water, then it will go to the bottom and reach. Okay, that is the first case. Density of the solid is greater than density of the liquid. The example. Next, second case is that it should not sink down, but it will sink up to the surface, and inside that surface it will float. That is, the example is the density of water should be is equal to here density of solid. Best example is ice cubes. Ice cubes. I observed ice cubes. Ice cubes will float, but it will not go to the sink, not go to the bottom, but it will not. It will sink. It will sink, and inside the liquid it will float, but it will not go to the bottom of the container. That means if the ice is ice cubes, you can take ice cubes, keep inside the water, then ice cubes will float just inside the water. Okay, because ice cubes density almost all equal to density of water. That means density of water is 1 gram per cc, whereas density of ice is 0.8 to 0.9 gram per cc. 0.1 difference will be there, density of ice. That's why it will float. So that is about second case, where the density of solid is equal to density of liquid. Next, case 3. Case 3, if density of solid is less than density of liquid. Density of solid is less than density of liquid. Are you able to following? Nobody reacting? Please react, any one of you? Yes or no? Muneshwar, Gautam Venkat? Yes, very good. Right. So third case is that, third case, if the density of solid is less than density of the liquid. The density of solid is less than density of the liquid, what happens? See, density of solid is less than means it is completely float on the surface of the liquid. That means you can imagine like this. That means the weight of the body is less than upthrust force. Weight of the body is less than upthrust force. Then in such a situation, you can imagine the solid body will be slightly or small, slightly will be immersed or sometimes completely float. You can imagine the object will be like this. Completely float onto the surface of the liquid. Okay, so this is the floating condition. So weight is less than upthrust force. So that object simply float on the surface of the liquid. But sometimes slightly will immerse, lightly. A small amount of volume will be immersed also. But still, weight will be balanced the upthrust force. Okay, so this is about the third condition. If the density of the solid is less than the density of the liquid, then what happen? The weight will be less than the upthrust force. In that case, the body is partially immersed or completely upside also sometimes we can observe. Okay, so in this case you can observe weight of the body is equal to W is equal to mg, where density rho into volume v, rho vg. Okay, suppose if it is partially immersed, suppose a small amount is immersed here, suppose, then you can say v in inside immersed volume, you can take v in, then fb is equal to, that is upthrust force, v inside into sigma into g. volume immersed, that much amount of weight only it will be displaced. Volume immersed V inside into sigma into J. In that case, rho Vg will be equal to V inside into sigma G. That means weight W is equal to Fb, upthrust force. That implies rho Vg is equal to V in into sigma G. Are you clear this? Where V in is the volume just immersed inside the liquid, V is the total volume of the body, rho is the density of the solid, G acceleration due to gravity, sigma is the density of the liquid. From this we can calculate how much amount of volume is inside or immersed into the liquid. For that you can calculate Gg cancel, then V in is equal to rho by sigma into V. V in is equal to rho by sigma into V. If you know the volume of the body, if you know the density of the solid and the density of the liquid, then you can calculate how much amount of immersed, how much amount of volume immersed inside the liquid. Still it is in the flotation condition. Okay. So in this case, what is the apparent weight of the body? Anybody can say? The body is in floating condition. What is the apparent weight of the body? Here apparent weight of the body is equal to 0. Because apparent weight means what I said, apparent weight is equal to weight of the body minus upthrust only. Weight of the body minus upthrust. Because weight is equal to upthrust, then weight minus upthrust is equal to 0. That means W apparent is equal to 0. Apparent weight of the body is equal to 0. Okay. So in this condition, this is the equilibrium condition. So at this equilibrium, for a floating body, okay, so here simply will be balance the weight of the body is equal to buoyancy force. Weight of the body is equal to buoyancy force. Okay. Are you clear this up to? So this is about a translational equilibrium. This is about translational equilibrium for the flotation. Next we will go for rotatory equilibrium. Next we will go for rotatory equilibrium. Okay. I will go for second type, rotatory equilibrium. Where we can see rotatory equilibrium or rotational equilibrium, or also you can say rotational equilibrium also you can say. Rotational equilibrium. Suppose you can observe a simple boat. Anytime have you traveled in the boat? So they will say a small boat, people has to sit inside the boat, not stand at the edges or at the middle, at the end points. Okay, the boat drivers will say don't stand. Okay, because if you stand all the people, then the center of gravity will be shift upside. Then if slightly bent also, then just try to make the torque to rotate the body. That means it is flipping. That means simply topple the boat. That will make the simply all the people will go into the water. Okay, so that means the boat should be in rotational equilibrium. Then only it will float. Or else you can take you have a big log, okay, a tree log you can take, you know the tree log, the body part of the tree. So this tree log you can keep inside the water. Okay, one situation is vertically, another situation is horizontally. In which case it will be in floating condition? Anybody can say whether it will float vertically or horizontally, the tree log?
Sir, horizontal.
Horizontally. Why it will not float vertically? Yes, it will not float vertically because The problem is rotational equilibrium. Simply a small tilt also happen, a small tilt in the log also, that will make the rotational effect, so that it will comes down like this. Okay, that means it is a unstable equilibrium vertically. Whereas in the case of horizontal, it will have a stable equilibrium. Okay, so the center of gravity will be shifted. That we will discuss now. So that is about concept of rotational equilibrium. Rotational equilibrium. Okay, are you clear this? So in this mainly what are the things will be there? I will tell you in rotational equilibrium. So when a body can take simply a simple container. Inside the container there is a small body you can keep, partially immersed and floating. So the body can take like this. This is the body. This is the body, suppose. Okay, it is in floating condition. Now, so this is the center of gravity where we can place. So there is a line you can observe vertically. This is the line. There is a vertical line passing through center of gravity. This is the vertical line. So in this vertical line, there is at some point you can observe. At some point you can observe center of gravity here. At some point here is the CG. Center of gravity you can observe. Here a point is called G point, center of gravity point. Then we have buoyancy force point also. Force of buoyancy acting vertically up. Actually from the point G, weight acting vertically down. Means here from this point weight acting like this, mg from point G. And vertically upward we have thrust force, upthrust force or buoyancy force. So like this it will act, buoyancy force. And at this point FB will act like this. So where is this point? We can expect below the center of gravity actually. It is floating means that is called point B. That is the buoyancy force point. Both are along single vertical line, but point B should be downside and normally point G slightly upside. Okay. So this normally can observe. So that FB will balance the weight so that it is floating. FB is equal to mg. Okay. Now, suppose if it is shifted slightly towards right or left, what happens? Suppose you can see here in this diagram. So you can draw the same diagram slightly shifting. So I'll draw the diagram. So this is the shifting diagram. Slightly shifting means bending, sorry. Slightly it will bend. You can see the diagram. Yeah, this pink color I used this. You can see this is the bent diagram by bending this log. Okay. Then again there is another line passing through its center. Okay. That line you can say like this. This is the line passing. Okay. Now you can observe what if the shift is G and shift in B. So now B will become B dash somewhere here. This is the B dash. Okay. Then B dash, from this B dash, buoyancy force will act vertically up. This is the buoyancy force diagram. B dash in this condition. Now, see here, this line, this vertical line, dotted line, and this B dash line will intersect. This intersection point you can call it as M, meta center. The intersection point is called M, that is meta center. Okay. Now we have G center and B center and meta center. So that intersection point is meta center, and the G center you can observe here below this meta center, somewhere here. This is G center. So here G center, from the G center, force acting vertically down, downside, mg, and from B and meta center along the same vertical line you can observe, because the M is intersection point only I have taken. So that meta center are force acting vertically upward. This FB dash acting vertically upward. So that means now you can observe, if meta center is above the point G, condition is that if meta center M above G, center of gravity, above center of gravity, then the torque or couple will act, the torque, this FB will try to bend like this towards left, right to left, the log, whereas G will make like this. The couple will act like this with respect to meta center. FB will make towards left from right to left, whereas this G, center of gravity, will make from left to right. So that makes what happen? Again, this log will comes to its original position. This log will comes to original position, vertical body. Okay, that is called tilting back into original position when meta center above the center of gravity. In some cases, the meta center will come down and center of gravity will go up. When the center of gravity will go up, I said now, a log is placed vertically balanced condition. In that case, the center of gravity will be above the meta center, because above the surface of water also there is so much mass is available. So that center of gravity will be shifted to above the meta center. Or on the top of a boat, if people are standing, then people's mass is shifted above the water level, so that center of gravity will be shifted upside. Then in that case, meta center will come down, center of gravity will go up. Then second diagram will be similar diagram. Only difference is that I am drawing this. This is the again tilted log only. You can take tilted body with respect to original body. Okay. So this line will be there, force line. So here in this case meta center will come down. That means suppose because of mass is above the surface of water, center of gravity will go up. Okay, somewhere buoyancy force here at this point, then buoyancy force line will be like this. The intersection of this initial line and final line, this will give meta center. Then this meta center below the center of gravity, you can see here, below the center of gravity. Buoyancy force B also below the line. Then from the center of gravity, weight acting downwards, this mg. From the buoyancy force, FB acting vertically up. Then what happens here? This makes the rotation towards the right, this side. Okay, this is like clockwise torque. Here anti-clockwise torque, ACW. Here CW, clockwise torque. Then the clockwise torque, what makes it object? Clockwise torque object to fall down. So that is called, we can say, okay, exactly the name is called capsize. That means cover turn. Okay, the object will capsize or cover turn. Okay, so that is called flipping also, flipping. So here see FB will make the clockwise torque. Here you can see here G will make this side clockwise torque. Then in that case, this is unstable equilibrium. This is unstable equilibrium. This is the cover turn or capsize. Okay, and it won't comes back to original position. The body won't comes back to original position. This is unstable. Are you clear this? Rotation equilibrium conditions. One is a stable equilibrium. Even though if it is small tilt is there, it comes back. Okay. Whereas in unstable equilibrium, if it is small tilt is there, then it will take the cover turn. Then the body will take upside down, or suppose vertical body will fall down, or sometimes body will be turn up, capsize. That means you can see the boat will topple like this. The boat will be topple. So you can see that in the case of boat, it will topple down. The boat will topple down. In this case, boat will topple down. Toppling will be happen. Okay. So this is the case we have to understood. So this is about understanding about rotational equilibrium. Two important cases. One is meta center and center of gravity. These two important points. The intersection of initial line and inclined line, that is the meta center. Then meta center is above the center of gravity, then it will tilting back above first case. Okay, next case, if meta center M is below center of gravity, M is below G, below center of gravity, then it will topple or it will cover turn. It is the unstable rotational equilibrium. Okay. So keep in mind these 2 points. One is meta center above the center of gravity, it will be stable and no problem. And if M is below the center of gravity, then it will make the cover turn and unstable equilibrium and the object will topple. Okay. So this is about understanding about rotational equilibrium. So there are two cases we discussed here. One is a translational equilibrium, second is a rotational equilibrium. Are you clear this up to?
Yes, sir.
Right. So next, we have 3 more minutes. So in translational equilibrium, we can have certain applications. So applications of translational equilibrium, you can see. Applications of translatory equilibrium. In this, already we said V inside of the body. V in what I said? V, a body, suppose a density, a solid body of density rho, okay, partially or fully immersed inside the liquid of density sigma. In that case, what I said, V rho g is equal to, that means weight of the body is equal to V inside sigma g, where sigma is the density of liquid, where V inside is the this much. How much amount of immersed, that is V in. Then from this we can calculate Gg cancel. V in is equal to V into rho by sigma. This is the amount of volume inside the liquid. Then amount of volume outside the liquid, how to calculate? V out is equal to total volume minus V inside. That is equal to V minus V rho by sigma. That is equal to V common 1 minus rho by sigma. So this is the amount of volume of the body which is outside the liquid while it is in floating. Similarly, from above equation 1, we can calculate, okay, the fractional amount of volume inside the liquid, that is V in by V. V in by V is equal to rho by sigma. Is the fractional amount of volume inside the liquid. Similarly, you can calculate fractional amount of volume outside the liquid. V out by V is equal to 1 minus rho by sigma. Fractional amount of volume inside the liquid you can calculate. Fractional amount of volume outside the liquid you can calculate. Okay. Then we can go for application 1. So body is floating. Okay, we know V inside and V outside. Okay, by observing you can calculate. Then you can calculate the density of the liquid. How to calculate? By using equation 1. By equation 1, if you don't know the density of the liquid, from this density rho, density of the liquid is equal to V in by V into sigma. V in by V into sigma. That means if you know the density of liquid, okay, and amount of volume inside the liquid, you know, amount of volume of body is know, then we can calculate the density of solid. That is the first application. To calculate the density of solid without knowing its mass, simply by knowing its amount of volume inside the liquid. Are you clear this? That is our first application. Second application we can go for. We have two different objects. And from that you can calculate a ratio of their densities also. Already we know that formula, row one density, then from the second density also can calculate. Okay, that is one more application. Next one more application is there, we'll discuss later about that. So up to 1 minute is less than. So thank you very much. Okay.